Chapter 10. Fun with Magnets. How magnets were discovered. A magnet is an object or material that produces a magnetic field. It can attract certain materials, such as iron or steel, and exert a force on them without physically touching them. Magnets have two poles, commonly referred to as the North Pole and the South Pole, and they exhibit a variety of properties, including attraction and repulsion between poles of different or like polarities, respectively. The discovery of magnets dates back thousands of years. The ancient Greeks and Chinese civilizations were among the first to observe the natural occurrence of a specific type of rock that possessed magnetic properties. This rock, known as lodestone or magnetite, is an iron oxide mineral that exhibits magnetic properties. The exact circumstances of the discovery of magnetism are not well documented, but it is believed that the ancient Greeks and Chinese noticed that certain naturally occurring stones, such as lodestone, had the ability to attract iron objects. The Chinese are thought to have used magnetism for navigational purposes as early as the 4th century BCE, employing compasses made of magnetized lodestone. One of the earliest documented studies on magnetism is attributed to the Greek philosopher Thales of Miletus around the 6th century BCE. He discovered that a piece of lodestone, when suspended, would align itself with Earth's magnetic field and point in a consistent north-south direction. This property of magnetism was further investigated and studied by other Greek scholars, such as Plato and Aristotle. The understanding of magnets and magnetism continued to evolve over the centuries. In the 16th century, William Gilbert, an English physician and scientist, conducted extensive experiments and investigations on magnets. He published his findings in a seminal work called The Magnet, in which he established the concept of the Earth as a giant magnet and introduced the terms electricity and magnetic pole. Since then, scientific knowledge about magnets has expanded significantly. Today, magnets are widely used in various applications, including electrical generators, motors, magnetic storage devices, speakers, medical equipment, and many other technological devices. The discovery of magnets and their properties has played a crucial role in shaping our understanding of physics and has led to numerous practical applications in modern society. Magnetic and non-magnetic materials. Materials can be broadly categorized into magnetic and non-magnetic based on their response to magnetic fields. Here's a breakdown of each category. Magnetic materials. Magnetic materials are substances that can be magnetized or attracted to a magnet. They can produce their own magnetic field and interact with external magnetic fields. Magnetic materials can be further classified into three groups. A. Ferromagnetic materials. These are the most common type of magnetic materials. They exhibit strong magnetic properties and can retain their magnetization even after the external magnetic field is removed. Examples include iron, nickel, cobalt, and their alloys, such as steel. B. Paramagnetic materials. Paramagnetic materials are weakly attracted to magnets. They become magnetized when exposed to an external magnetic field but lose their magnetization when the field is removed. Substances like aluminum, platinum, and oxygen are paramagnetic. C. Ferromagnetic materials. Ferromagnetic materials exhibit magnetic behavior similar to ferromagnetic materials but have two different types of magnetic icons in their structure, resulting in a net magnetization. One example is magnetite, Fe3O4. Non-magnetic materials. Non-magnetic materials do not exhibit significant magnetic properties and are not attracted to magnets. They either have no response to magnetic fields or have very weak interactions. Some common non-magnetic materials include wood, plastic, glass, rubber, copper, aluminum, in its pure form, and most non-metallic substances. It's important to note that the magnetic properties of a material can depend on various factors, such as temperature, impurities, and the presence of external magnetic fields. Some materials may exhibit magnetic behavior under specific conditions while behaving non-magnetically under different circumstances. Additionally, there are also materials with intermediate magnetic properties, such as antiferromagnetic and diamagnetic materials, which possess unique magnetic behaviors that differ from those of ferromagnetic, paramagnetic, or non-magnetic substances. Poles of magnet. A magnet has two poles, commonly referred to as the North Pole and the South Pole. These poles are fundamental characteristics of magnets and play a crucial role in their magnetic behavior. Here's a closer look at each pole. North Pole. The North Pole of a magnet is labeled as the N or N pole. It is conventionally considered the seeking or north-seeking pole because, in the presence of an external magnetic field, it tends to align itself in the direction of Earth's magnetic north pole. Therefore, the north pole of a magnet is attracted to the south pole of another magnet or to the north-seeking pole of Earth's magnetic field. South Pole. The south pole of a magnet is labeled as the S or S pole. It is considered the seeking or south-seeking pole because it seeks to align itself with Earth's magnetic south pole in the presence of an external magnetic field. Consequently, the south pole of a magnet is attracted to the north pole of another magnet or to the south-seeking pole of Earth's magnetic field. The behavior of magnets can be summarized by the fundamental principle known as the like poles repel, opposite poles attract. This principle states that the north pole of one magnet repels the north pole of another magnet, while the north pole of one magnet attracts the south pole of another magnet, and vice versa. It's important to note that the magnetic field lines generated by a magnet extend from the north pole to the south pole in a loop, forming a closed magnetic circuit. The field lines exit the magnet from the north pole and re-enter through the south pole. The strength of the magnetic field is generally strongest near the poles of a magnet. Understanding the properties and behavior of the poles of a magnet is essential for applications involving magnets, such as the construction of motors, generators, magnetic storage devices, and magnetic resonance imaging (MRI) technology, among others. Finding directions with the help of magnet. Finding directions with the help of a magnet is possible by utilizing the magnetic properties of a magnet and its interaction with Earth's magnetic field. Here are a few methods commonly used. Magnetic compass. A magnetic compass is a traditional tool used for navigation and determining directions. It consists of a magnetized needle, which aligns itself with Earth's magnetic field. The needle is typically marked with the letters N for north and S for south. When the compass is held horizontally, the needle points towards the Earth's magnetic north pole, providing a reference for determining directions such as north, south, east, and west. Floating magnet method. In this method, a small magnet is attached to a lightweight object, such as a piece of cork or a leaf, and placed on the surface of calm water. The magnet aligns itself with Earth's magnetic field, causing the floating object to orient itself in a north-south direction. By observing the orientation of the floating object, you can determine the approximate north-south direction. Sun and shadow method. This method utilizes the fact that the sun rises in the east and sets in the west. When using this method, you need to have a clear view of the sun. Place a stick or a straight object vertically in the ground and mark the tip of the shadow cast by the stick. After some time, mark the tip of the shadow again. The line connecting the two marks will be an approximate east-west line. If you face the line perpendicularly, with the first mark on your left and the second mark on your right, then the direction you are facing is approximately north. It's important to note that these methods provide approximate directions and may be influenced by local magnetic anomalies or deviations from true north. For precise navigation, it is recommended to use advanced tools like a GPS, global positioning system, device or consult detailed maps and compasses calibrated for magnetic declination, which accounts for variations in the angle between true north and magnetic north at a specific location. Using a magnet for finding directions is a practical and useful technique, especially in situations where traditional navigation tools may not be available or reliable. Make your own magnet. Creating your own magnet can be done by following these steps. 1. Select a ferromagnetic material. Start by choosing a ferromagnetic material, such as iron, nickel, or cobalt. These materials have the ability to become permanently magnetized. 2. Prepare the material. Take your chosen ferromagnetic material and shape it into a small rod or bar. You can use a file or sandpaper to smoothen the surface. 3. Magnetize the material. A. Stroke method. Hold the ferromagnetic material in one hand. Take a strong magnet, e.g., a neodymium magnet, on the other hand. Starting from one end of the material, stroke the magnet along the length of the material in one direction. Repeat this stroking motion in the same direction multiple times, always starting from the same end. This aligns the magnetic domains within the material, creating a magnetic field. B. Electromagnet method. Alternatively, you can create a temporary magnet using an electric current. Wrap an insulated wire around the ferromagnetic material several times to create a coil. Connect the ends of the wire to a battery or power source. When the current flows through the coil, it generates a magnetic field, magnetizing the material. However, once the current is turned off, the magnetization will be lost. 4. Test the magnetization. After magnetizing the material, you can test its magnetic properties. Hold the material near small metal objects, such as paperclips or safety pins, and observe if it attracts them. If the material attracts the objects, it indicates successful magnetization. It's worth noting that creating a strong permanent magnet at home can be challenging. Professional magnets are typically manufactured using specialized processes that align the magnetic domains in a precise manner to achieve maximum magnetic strength. The methods described above are simple demonstrations to create magnets with modest magnetization. Remember to exercise caution when handling strong magnets, as they can snap together or attract nearby metal objects forcefully, potentially causing injury or damage. Attraction and repulsion between magnet. When two magnets come close to each other, they can either attract or repel each other, depending on the orientation of their poles. The interaction between magnets is governed by the fundamental principle known as, like poles repel, opposite poles attract. Here's a breakdown of the attraction and repulsion between magnets. Like poles repel, when two magnets have their like poles facing each other, such as two north poles or two south poles, they will repel each other. The magnetic field lines produced by each magnet push against each other, creating a force that pushes the magnets apart. The repulsion between like poles is stronger when the magnets are closer together. Opposite poles attract. When two magnets have their opposite poles facing each other, such as a north pole and a south pole, they will attract each other. The magnetic field lines produced by each magnet interact and align with each other, creating a force that pulls the magnets together. The attraction between opposite poles is stronger when the magnets are closer together. The strength of attraction or repulsion between magnets depends on various factors, including the magnet's magnetic field strength, the distance between the magnets, and the sizes of the magnets. Stronger magnets with larger magnetic fields will exhibit more significant attraction or repulsion. It's important to note that the force of attraction or repulsion between magnets decreases with distance. As the distance between magnets increases, the strength of the magnetic field interaction decreases, resulting in a weaker force of attraction or repulsion. The phenomenon of attraction and repulsion between magnets forms the basis for various applications, such as magnetic closures, magnetic levitation systems, and magnetic locks. It also plays a fundamental role in the operation of electric motors and generators, where the interaction between magnetic fields creates rotational motion and converts electrical energy into mechanical energy, and vice versa. A few cautions for magnet. When working with magnets, it's important to exercise caution due to their strong magnetic fields. Here are a few precautions to keep in mind. 1. Pinching hazards. Strong magnets can exert a significant force, and if two magnets or a magnet and a metal object snap together, they can pinch fingers or skin. Be careful when handling magnets and keep them at a safe distance from each other to avoid pinching accidents. 2. Projectile danger. Magnets can attract metallic objects from a distance. Keep magnets away from sensitive electronic devices, credit cards, pacemakers, and other magnetic sensitive items to prevent damage or interference. 3. Breakage. Some magnets are brittle and can break easily if dropped or subjected to impact. Broken magnets can have sharp edges and small pieces that can pose a risk of injury. Handle magnets with care and avoid dropping them. 4. Swallowing hazard. Small magnets can be a choking hazard and dangerous if swallowed. Keep magnets out of the reach of young children and pets to prevent accidental ingestion. If ingestion occurs, seek medical attention immediately. 5. Magnetic fields. Strong magnets can interfere with sensitive electronic equipment, such as pacemakers, computer hard drives, and credit cards. Keep magnets away from these devices to avoid potential damage or malfunction. 6. Eye protection. When handling strong magnets, particularly ones that can snap together forcefully, wear protective eyewear to prevent injury in case of unexpected movement or pinching accidents. 7. Secure storage. Store magnets in a safe and controlled environment, away from sensitive equipment and objects that can be affected by magnetic fields. Keep magnets away from credit cards, electronic devices, and any magnetic-sensitive materials. 8. Magnetic fields in health. While everyday magnetic fields pose no significant health risks to most individuals, extremely strong magnetic fields, such as those found in medical MRI machines, require appropriate precautions and should only be used under the guidance of trained professionals. By following these precautions, you can safely handle and work with magnets, minimizing the risk of accidents or damage. Always use common sense and exercise caution when dealing with magnets, particularly powerful ones, and seek professional guidance when necessary.